We're now moving into the second half of this full-year course, with a topic that is more purely probabilistic than any that we've considered before: conditioning. Now, I'm not going to lie to you. This is usually the trickiest topic for students when first encountering it in this course. It certainly was, and to a certain extent still is, for me. Roughly speaking, there are two kinds of probabilists. There are people who approach probability with the tools of analysis and slowly and painfully develop some probabilistic intuition from there. That's me. And then there are people who are truly gifted with probabilistic intuition from birth. I affectionately call those people real coin tossers. And this is the topic that really shows which group you might be in. You can succeed in probability no matter whether you're a real coin tosser or not. I'm going to take an approach to conditional probability founded in my analytical thinking, and I hope that it will appeal to you too. We've already seen the basic notion of conditional probability on an early homework problem in this course. Given a probability space and an event B with strictly positive probability, we can use it to form a new probability measure on the same sigma field. I'm calling it PB here, although another notation for it that's quite common is probability given B of another event A, and that's simply defined to be the probability of A intersect B divided by the probability of B. It's easy to get bogged down in lots of calculations in conditional probability, and so it's convenient not to have to write those intersect signs. Sometimes we will write A intersect B simply as a kind of product, A times B. We often think of conditional probability intuitively in terms of a two-stage experiment. In the first stage of the experiment, we see whether one particular event has occurred or not. And if it has, it may influence whether a second event we're going to measure in a second stage will occur or not. Therefore, we may want to update our information, our probabilities of the later events, given information about whether the earlier event has occurred or not. In this language, we'll refer to the original probability measure as the prior probability of an event, and after we observe that event B has occurred, we refer to the new updated conditional probability as the posterior probability of that same event. Now, in discrete and usual statistical contexts, it's very common to combine different conditional probability measures together, where we take the sample space and partition it into a finite or perhaps countable collection of positive probability events, and then look at the conditional probability measures for each of those events put together, since those measures are supported on disjoint events. There are two very elementary but extraordinarily important results that come from that line of thinking: the so-called law of total probability and, most critically, Bayes' theorem. Although these are topics that are normally taught at a lower division undergraduate level, they are important enough that I'm going to include a lecture on them right now. So you're now going to see an excerpt from a podcast in Math 180A, the undergraduate probability course that I taught in fall 2019, elucidating these ideas. If you have a partition of your probability space, a partition of your sample space, into positive probability bins, B1 through Bn, then you can measure the probability of any event by adding up the probabilities of the pieces of that event in each of the bins, and each of those can be calculated from the definition of conditional probability like this. And that's a very useful way to compute if it's easy to tell what the probability of A given B is for each bin B. And here was a kind of typical example where that can be used. Suppose that you know that the coins that are in circulation are largely fair, but there are some slightly biased ones and an even smaller population of extremely biased coins, and you happen to know the prior probabilities, that is, what proportions of them are biased by how much. Then you can use this to figure out, if you take a random coin and you don't know from which bin it came, you don't know whether it's fair, biased, or very biased, you can figure out what's the probability that it will come up heads. Okay, that is, this information here, that 90% of coins are fair,
is the statement that if we let B1 be the set of fair coins, the probability of B1 is 90%. And the fact that it's fair is the statement that if A is the event that it comes up heads, the probability of A given B1, given that you're a fair coin, is exactly 50%. On the other hand, we're told that 9% of coins come up heads 60% of the time. That is exactly the statement that if B2 is the event that the coin is 60% towards heads biased, then B2 has probability 9%, and that the probability of heads given that you chose B2 is 60%. And the same with B3, the heavily biased 1% of coins. And putting that information together, we can just calculate that the probability of A, using exactly the law of total probability, adding up those three numbers multiplied together, in each case, gives us 51.2%. Okay, so the overall, the sort of average coin is slightly biased toward heads. So that is the law of total probability and a canonical way it can be applied. But there's a more subtle and interesting question that you can ask, which turns this on its head. No pun intended. Pun totally intended. Yeah. Which is, okay, same setup. We happen to know that there's this population of coins out there, 90% are fair, 9% are slightly biased, and 1% are heavily biased. And now you pick up a random coin on the street. I'm not going to ask you what's the probability it comes up heads. I'm going to have you flip it and notice that it came up heads. And then I want to ask you, which bin did it come from? Was that a fair coin, or was it a biased coin, or was it a heavily biased coin? Of course, there is not enough information to answer that. You don't know. But what we can answer is what's the probability that it was a fair coin? Or what's the probability that it was a heavily biased coin, etc. Okay, so how likely is it that that coin came from the heavily biased bin? Now, without any information, without flipping it and seeing whether it came up heads or tails, you only know the priors. You know that there was a 1% chance a randomly chosen coin was biased heavily. But now you have some additional information. It came up heads. Does that tell you anything, and how much does it tell you? What we're asking about now is, what is the probability that it is heavily biased, given that it came up heads? That's what we're asking right now. And what we know is that the probability that it comes up heads, given that it's heavily biased, is 80%. That's what it means that it's biased, 80%. And you should not confuse those two numbers. The probability of B given H is not the probability of H given B. In fact, they may not be really related in any strong way, as we're going to explore right now. This is really important. Do not confuse the probability of A given B with the probability of B given A. They're not reciprocals of each other. They're not equal. We're going to see in a moment a general way, when you have a partition like this, that you can calculate one from the other plus extra information. But the good example to keep in mind always is this one. According to Forbes magazine, here's some real data. As of April of this year, there were 2,208 billionaires on Earth, and 1,964 of them were male, which is exactly to say that the probability that you're male, given that you're a billionaire, is the ratio 1964 over 2208. Almost a 90% chance. Almost 90% of all billionaires are men. However, the probability that you're a billionaire, given that you're a man, is most definitely not 89%. Okay? The probability that you're a billionaire, given anything, is a tiny, tiny number, because there are only a little over 2,000 billionaires out of almost 8 billion people. That's the thing to keep in mind. Reversing conditionals will only lead to misery. Quite literally, you should look up online the prosecutor's fallacy. Unfortunately, this fallacy of reversing a conditional has been used to imprison and prosecute many innocent people over the years. So don't do it. Okay? So here is how we can actually calculate the probability of B given A, knowing information about the probability of A given B. Bayes' rule, okay, is the following calculation, which applies in the case where we've been working with, in the law of total probability, where we have a partition of our sample space into positive probability bins, events. So suppose I have a partition of possible events, B1 through Bn. Exactly one of those events happens. Okay, they're a partition. And I'd like to calculate the probability of B1 given some event A. And what I know is the probability of A given B1. And here's how you can calculate that using the law of total probability. The probability of, let's just take k to equal 1 in this calculation. The probability of B1 given A, well, by definition, that's the probability of B1 intersect A divided by the probability of A. Now, the top, probability of B1 intersect A, now I can reverse that, because intersections are commutative. A intersect B is the same as B intersect A. And so that first line on the top is just, I can write that from the definition of conditional probability as the probability of A given BK times the probability of BK. But we still have the denominator there, the probability of A. How can I figure out that? Well, that's exactly what the law of total probability tells us, that, oh, that I can calculate by expanding out over the intersection of A with all the bins and doing the conditional probability calculation. This is Bayes' rule, and this is how you can calculate the reverse information. What's the probability that you were in one of the bins given the information of the outcome? Okay, so let's look back at the coins example. What we wanted to calculate there was the probability that it was the heavily biased coin. I'll call that C80, the coin with probability 80% of coming up heads, given that heads came up. And Bayes' rule tells us the way we should calculate this is to say, okay, first, from definition, that's the probability of the intersection of those two events divided by the probability of heads. Okay. And actually, we already calculated the probability of heads on the last slide, but I'll sort of do it again here. And now that is the probability of H given C80 times the probability of C80 divided by the probability of H. Now, we could go one step further, like it says to do up here, and expand that denominator using the law of total probability, which means, oh, I calculate that as the probability of heads given a fair coin times the probability of the fair coin being the one that was chosen, plus the probability of heads given the slightly biased coin times the probability that the slightly biased coin was the one that came up, plus the probability of heads given the heavily biased coin times the probability that the heavily biased coin was the one that came up. Okay. Now that calculation in the denominator is exactly what we did on the previous slide, and we got the answer for that, I'll just quickly swipe back, was 51.2%. So we don't need to redo that calculation. The denominator is 51.2%. The numerator up here is the probability of heads given that it was C80. The probability of heads given that we chose the heavily biased coin, which by definition is 80%, times the probability that it was the heavily biased coin, which was 1%. So I have to multiply 0.8 times 0.1, divide it by 51.2%. And when you do that, what you get is about 1.56%. Now that's still a small number, but it's bigger than the prior 1%. We knew that without any information, the proportion of heavily biased coins in the population was 1%. Now having the new information that we did come up heads, our posterior probability that it was, in fact, the biased coin that we flipped increases a little bit. It's still most likely that it was a fair coin, and more likely that it was slightly biased than heavily biased, but it's more likely than it was without any information that it was the heavily biased coin. Okay, so that's Bayes' rule. And let's do another example to demonstrate how to use it. But before we do the example, let's start by testing our intuition. Here is a typical kind of Bayes' rule application from epidemiology. So suppose there's an HIV test that is 99% accurate. And actually, the accuracy of medical tests are usually reported in the literature with two numbers. There's the false positive rate and the false negative rate. False positive rate means that you don't have the disease, but the test indicated that you do. And false negative means that you do have the disease, but the test indicated that you don't. There's no reason those two numbers have to be equal. Okay, that's just the design of the test. But to make things simple, we'll assume that this test has the same accuracy for both. If you come in and you have HIV, 1% of the time it will say you don't. 99% of the time it will say you do. Whereas if you come in and you don't have HIV, 99% of the time it will say you don't, but 1% of the time it will give a positive result. And for reference, this is another accurate number. As of this year, 0.33%, a third of 1% of the population of the United States are HIV positive. So suppose that you come in randomly off the street and take this test. The question is, if the test is positive, the test comes back and says positive for HIV, how likely is it that you are HIV positive? How likely is it that you have the disease? Okay, this is just like the coins question. We know that the result was heads. Now we know that the result was the test was positive. How likely is it that you actually have the disease? The correct answer is C, 25%. It's actually 24.7, as we'll see in a second. Okay, but this is a great example of counterintuitive nature of conditional probability. And let me tell you that I didn't make this example up. I actually took it from medical literature where a paper was talking about asking physicians this question. So a group of over 800 physicians, this was 15 years ago now, were asked this question. Okay? And a plurality of them, the most popular answer was A. Practicing physicians who are giving their patient life-changing medical advice got this wrong. Don't do that. So the answer, surprisingly, if you haven't thought about these sort of things before, is 25%. Even though the test is 99% likely to give a correct result, if you get a positive result here, the chance you have the disease is only about 25%. Let's figure out how that can be, why that is. So let's write this down. What you need to do is translate this information into probability theory. So there's two events we're interested in. The event T, that you get a positive test, and the event H, that you indeed have HIV. And what is the information we're given? We're told that the chance of a false positive is 1%. That means the probability that the test is positive, given that you do not have HIV, given H complement, is 1%. And similarly, that the probability that you test negative, given that you have the disease, is 1%. And then the other piece of information we're given is that the overall chance in the population that you have HIV is 0.33%. Okay, now we're going to answer this by using Bayes' rule. And Bayes' rule requires you to have a partition of the sample space, but the standard partition you use when you have a single event like H that you're interested in here is that the sample space divides into H and H complement. Everyone is either HIV positive or HIV negative. And so therefore we can compute that the probability that we're interested in, what is the likelihood that you have the disease given that you tested positive? Okay. Well, we say, that's by definition the probability of H intersect T divided by the probability of T. The numerator we write as, in the reverse order, the probability of T given H times the probability of H. And all of that is divided by, okay, we have a partition of two things, so there's going to be two terms in this total law of total probability sum. Probability of T is the probability of T given H times the probability of H plus the probability of T given H complement times the probability of H complement. Okay, and now we look for all of these terms in the data we have. Do we have the probability of T given H? We don't have it written down. What we have is the probability of T given H complement and the probability of T complement given H. But there is actually the information there because, remember, probability of blah given H is a probability measure. And that means that the probability of T complement given H is 1 minus the probability of T given H. Okay? So, when we look down here, I want the probability of T given H. That's 1 minus 1%, or 0.99, times the probability of H, which we're told right here is 0.33%, so 0.0033. And then I have to divide that by, well, the first term in the denominator is the same as in the numerator, so that's 0.99 times 0.0033. And then the second term, the probability of t given h complement, that is written right here. So that is 1% times the probability of h complement. Probability of h is 0.33%, so the probability of h complement is 1 minus 0.33%, or 99.67%. And now we just do that calculation, and if you do it, you'll see that it's 24.69%. 2 decimal places. Okay, that's how it comes out. That's the calculation. Do you understand better why it's true, or did the calculation just tell you that it's true and you're still confused? I'm willing to bet that almost nobody in the room feels more enlightened from this discussion about why some counterintuitive thing like this can happen. So I hope that this picture will help explain it better. The little ball is the set of HIV positive people, and the huge ball is the set of HIV negative people. This is approximately to scale in terms of area. The population of people who are HIV positive dwarfs the population of people who are HIV negative by a factor of 300, thankfully. Now, what we're told is that the test has a 1% false negative rate. That means that blue, being the color of testing positive, covers almost all of H. Okay, so the part of H that isn't covered by T is only 1% of it. And similarly, the part of H complement that is covered by T, the false positives, is only 1% of that giant ball. But 1% of that giant ball is much bigger than 99% of the small ball. And so the huge disparity in the sizes of the two partition bins biases the outcome. That's the problem, and that's what Bayes' rule can elucidate for us. Now, you can then ask, what's the point of taking an HIV test? And the point is twofold. First of all, you shouldn't trust, and a good doctor will not trust the outcome of one test. If it comes back positive, they'll send you for a different test, maybe using a different methodology. And also, if you do two tests that are independent from each other, that will bolster the results and improve this probability of having the disease given a positive outcome tremendously. But there's actually a step back we need to take, which is what Bayes' rule showed us is that when you have a huge disparity in the populations that you're interested in sizes, that size differential can heavily bias the outcome. But the truth is that if you're in your doctor's office asking for an HIV test, you're not a random person from the population. If you think you want to take an HIV test, it's because you have some other evidence that you might be HIV positive. Let's not get into what that evidence might be in this room. But if you already have some thoughts that you are in a smaller population of people who might be positive, that can change the results dramatically because of how sensitive this calculation is. And I'll just say you should, on your own, redo the calculation, supposing that the probability that you are HIV positive is 3%. Okay, suppose that you have a slight suspicion there might be some chance, and it's not, you have an elevated risk, 10 times the risk of the general population, but still a small number. How do you think that will change the posterior probability? I'll tell you that if you do this same calculation here again, but you replace the number 0.033 everywhere with 0.03, then you will get 75.3%. If you replace the number with 30%, suppose you think it's fairly likely, there's a 1/3 chance about that you have HIV. Still, that's not that likely, right? 2/3 odds, that doesn't sound so bad. What you'll get is that the calculation will tell you that the posterior probability is 97.7%. So by changing the sizes of those two populations that you're partitioning your set into, even a little bit, it dramatically changes the outcome of the Bayes rule calculation. So if you're in your doctor's office already, then you're probably not in that random sample population, which is why the doctor isn't totally wrong to think that the test should be more accurate than it is given a totally random sample. All right, let's do one more problem demonstrating how effective Bayes' rule is at explaining our intuition and how it can be so very wrong. So here's the Monty Hall problem. It's based on a real TV game show from the 1960s and early 70s, which was hosted by a Canadian game show host called Monty Hall, who only died 2 years ago. Apparently the best game show hosts are Canadian, because Alex Trebek is also Canadian, in case you didn't know. I'm Canadian, by the way. So here's a breakdown of how the end game on the show worked. The contestant who's made it this far in the game is presented with 3 doors and told that behind one of the doors there is a prize of great value, a car. But behind the other 2 doors, there's not anything of value. And in the way we explain this, it's usually goats. There are goats behind the 2 doors. You're going to choose one of the doors, and if you chose the door with the car, you get to keep the car. So you choose a door, and then, before opening the door to see if you got the car or a goat, Monty Hall says, hang on, I'm going to open one of the other 2 doors, and opens one of the other 2 doors to reveal a goat. And then comes back to you and says, let's give you a chance to change your mind. So let's suppose you chose door number 1, and Monty Hall opened door number 2. Monty will now ask you, we know there's a goat behind door number 2. Do you want to stick with door number 1, or do you want to switch to door number 3? You make that choice, and then the door you chose will be opened to see if you got the car. And the question is, should you switch? Will switching change the probability that you win the car? And if so, in a positive way. Should you switch? Yes, no, or it doesn't matter, it won't change anything. How many people think it just doesn't matter? Your odds are the same whether you switch or you stay. Let's raise the hands high, people. Have confidence in your answer no matter how wrong it is. Okay? Oh, I didn't mean to bias you there. Okay, so before I gave away that C is not the right answer, that was the most popular answer here, and that is the intuitive answer that most people give. The correct answer is A, you should switch. If you switch, you double your chances of winning the car. This is such a controversial statement that when this stylized form of the problem was written up in a popular statistics magazine, yes, there are such things, in the 1980s, there were hundreds of angry letters to the editor from professional statisticians disputing the calculation, saying, no, you're all wrong, you don't understand anything about Bayesian statistics. Clearly, the answer is C. And they were all wrong, because they were so biased by their intuition, they didn't think about this for even half a second. Okay, so let's think about it for more than half a second. Let's analyze this with Bayes' rule. So again, let's decide to call the door you chose at first door number 1. That's just our choice. We're calling it door number 1. You can think about it as the one on the left, but it doesn't matter. And that means when you choose door number 1, Monty Hall is not going to open door number 1, not until the end, if you chose that one at the end. So he is going to open door number 2 or door number 3. Okay? So we'll focus our analysis on the case that he chooses door number 2, but if he actually chose the other one, it's the same calculation again. So let's think of the events that we need to analyze here. Let's let B1 be the event that the car is behind door number 1, B2 is the event that the car is behind door number 2, and B3 is the event that the car is behind door number 3, and there's even odds that it's behind any one of the 3 doors. It's randomly selected which door it's put behind. So each of those events has prior probability 1/3. And then we're interested in the case that Monty Hall opens the second door, door number 2. Now, what's the information that we have here? So let's start with the probability of A given B2. A is the event that Monty Hall opens door number 2. And what's the probability of that given B2? B2 is the event that the car is behind door number 2. How likely is it that at this stage of the game he'll open the door that has the car behind it? 0. That's the trick here. That's why it's counterintuitive. He will never open the door with the car behind it unless you chose it at the end of the game. That's what biases everything and screws up our intuition. That's 0. And similarly, what's the probability of the event that Monty Hall chooses door number 2, given that the car is behind door number 3? That's 1. He will not open the door with the car behind it. And now the bit of information I haven't really given you is, what's this? The probability that Monty Hall opens door number 2, given that the car is actually behind the door that you chose originally. And here, we're just going to say 1/2. Let's say in that case, he chooses randomly between the two doors. Well, now we're set up to do Bayes' rule. What we're interested in is the probability that the car is behind door number 3, given that Monty opens door number 2. Because that will tell us whether we should switch. If that number comes out to be more than 1/2, then we should switch. If it's less than 1/2, we should stay, and if it's equal to 1/2, then it doesn't matter. So let's use Bayes' rule. This is the probability of the intersection of B3 and A divided by the probability of A. And to calculate the numerator, we expand that in the other direction using the definition of conditional probability. In terms of a number we do know, the probability of A given B3, and in the denominator, we have 3 terms. And all of those numbers are listed just above here, so let's sub them in. The numerator is 1/3 times 1. And the denominator is, well, that first term is the same as in the numerator, 1/3 times 1. The second term is 0, because that's 0. And the third term is 1/3 times 1/2. The 1/3s cancel, and we get 1 over 1 plus 1/2, which is 2/3. The probability, posterior probability, after this stage of the game, that the car is behind door number 3 is actually 2/3. And therefore, the probability that's behind the door you started with is 1/3. Therefore, you'll double your chances of winning the car if you switch. Now, by the way, there's a slightly deceptive but easier intuitive way to think about this, which is, look, at the beginning of the game, you chose a door randomly. What was your probability of winning the game at that point? 1/3. Now, if you don't switch, what's changed? Nothing. All that's happened is Monty Hall has given you more information about which of the other 2 doors it might be behind. So at the beginning, you made a choice, door 1 or doors 2 and 3. You chose door 1, giving you a 1/3 chance of winning. Now Monty Hall has eliminated one of doors 2 and 3 and shown you that the car is either behind that first one or the remaining one. There's still a 2/3 chance that it was over here, so there's actually a 2/3 chance that you'll win if you switch. Okay, now we all understand the Monty Hall problem, right? You're going to be able to go home and explain this to your parents and your friends, right? Because they are not going to get it. And believe me, the first time you try to explain it to somebody else, you're not going to get it either. It's really tricky. Question? Did they not notice on TV that people were not switching and losing more often? So statistical analysis of the hundreds of episodes of the show that that is indeed true, that these numbers are borne out in reality. But did anybody ever notice? No. And that is a sad statement that explains a lot of why the world is the way that it is.